Hi everybody, I'm Professor Rad, and today we're going to talk about finding critical values for confidence intervals. So let's get started. Let's begin with a critical value of a z-score. So if sigma is known, or if the population standard deviation is known, then the critical value we'll be using is a z-score. This is the same as the positive z-score we would use for a backwards middle problem. So let's just review that process here. It says find the z-score for 92% confidence interval. So I'm going to start out by drawing my curve to help me envision what's going on. And we'll put 0 in the middle. And then we have 92% in the middle 92%. Now what we're looking for ultimately is going to be the positive z-score here, but our process had us finding the negative z-score. So I'm going to draw the box there. Do you remember what we do next? So what we'll do is, in order to find this little white space here, we're going to take the whole area, which is 100%, subtract the percentage we know, and then divide by 2, because we have 2 little white areas here. So we can use our friend the calculator. 100 minus 92, divide that by 2, and we're going to get 4%. Now we really need this to be in decimal form, so 0.04, and then we'll add 2 zeros to the end so that it looks like the area that we're going to be looking up on our table. Then we grab our standard normal curve table, and we're going to look in the sea of numbers here for the closest to 0.0400. And when I'm looking that up, it looks like 0.0401 is the closest we're going to get. And that had a z-score of negative 1.75. So because we want the positive z-score for our critical value, we're going to get a positive 1.75. And there you go. That's how you can find our z-score. Same process as we've been using, just now for a middle percentage. Okay, so that will be implied if you have a certain percentage of confidence. Now, here's the good news. Okay, the good news is because we're going to be finding certain confidence levels frequently, we have another table here that's going to give us a shortcut. And the shortcut is all the way at the bottom. So at the bottom of this table, we have our various levels of confidence. And right above, we have our z-scores. So if I wanted to find, for example, a 90% confidence interval, for 90%, my confidence interval would have a critical value of 1.645. So the z-scores are right above those percentages. So you don't have to worry about going through and using the other table. So we have an example of using this new table. It says, let's find the z-score for 95% confidence interval. So I would go over to 95%, since that's my level of confidence, and I would get a z-score of 1.960. Ta-da! That's it. Now, I will point out that this first example we began with, using a 92% confidence level, if I go to my table, 92 is not listed. So if there's a percentage that isn't listed, you have to go back to the old method and use this table. But almost always, I'm going to give you one that's on here. In fact, for my class, I'm only going to give you one that's not on this list as like a bonus question. So conceptually, it's important to know that these z-scores come from a middle percentage. But in practice, when we go to find them, you can just use that bottom row. Now, in this situation, we use a z-score if we know sigma. Now let's think about what's going on for a moment. So when you create a confidence interval, it's because you don't know a population mean. So you are using sample mean to find a population mean. So if you don't know a population mean, it may be unlikely that you know a population standard deviation. That's probably not going to be known. Now, sometimes it might be. So for example, maybe we know that the heights of people are normally distributed and they tend to maintain the same standard deviation, like the same spread outedness. But over time, maybe that mean changes. It goes up or it goes down. People get taller over time or people get shorter over time. So if we want to figure out has like the mean shifted, but we know that the spread of the information stays the same, then we might use this technique here. But often we won't. So this presented a problem for statisticians. So there's a little bit of a story here. If you don't know sigma, then you cannot use the central limit theorem. If you don't know a population standard deviation, you can't use the central limit theorem. So that whole concept of the sample means are normally distributed is great, but it's not applicable if you don't have that population standard deviation. However, what's cool is an alternate technique was discovered by this man, William Seeley Gossett, and he developed this technique, which is very similar to the technique we use for our central limit theorem, and he called this the t-score. At the time that he developed this, he was working for Guinness. You know, the beer company. And so at the time he was hired by Guinness, there was a lot of competition among the beer companies. And they didn't want, their industry secrets getting leaked or sent elsewhere. So Gossett signed a contract with Guinness saying that he couldn't publish any of his findings under his own name. So he was forbidden from publishing it by the company. So he used a nom de plume. He used an alias student to publish his information. He was like, the world needs to know about this. So he published it under the name student. And thus this has become known as student's t-score. So it's not called student's t-score just because it's used in schools. No, this is used like out in the world, but it has the name student because of this little historical situation. So the good news is also that this method is really similar to the method that we've been using with the central limit theorem. All that's really different is how we're going to end up finding our t-score. So there's a lot of like heavy mathematical background stuff that's important, but for our purposes in terms of process, very similar. The small difference is that we'll need to find this new thing called degrees of freedom. And to find that, we're going to use the formula n-1. So if we all went out, we found samples of 40 people, our degrees of freedom would be 39. Now, our table is going to list the degrees of freedom on the side. So up here it says degrees of freedom, and you can see we're listing out several degrees of freedom. Now, we can't list out infinity numbers on a sheet of paper. So as you can see, the numbers keep increasing here until we get to about 37, 38, 39, then we get to 40, and then it starts to skip. Then we have 50, 60, 80, 100, and 200. So sometimes you might be working through a problem and your degree of freedom is not on the table. So let's say you have a degrees of freedom of 42. So then you would have to decide, do I use 40 or 50? Now in the case of 42, that decision is easy to make because 42 is pretty close to 40 and it would round to 40, so we would use that one. But let's say you had a degrees of freedom of 48. In that case, 48 is closer to 50, but I would still use 40. So because of the heavy mathematical machinery behind all of this, if your degrees of freedom is not on the table, you have to round down to the closest one that is. So let's fill in that blank in our notes. If the degrees of freedom are not on the table, you're going to round down. And the way that I remembered this as a student, it's kind of silly. I remembered that you can't claim to have more freedom than you have, right? You're only as free as you are. So if I have a degrees of freedom of 48, I can't claim to be 50 free, okay? I can do 40, but I can't do more than 48. So let's do some examples here. All right, first we're going to find the t-score for a 90% confidence interval with a sample size of 12. So this means that n is 12 and my confidence level is 90%. So first I have to find my degrees of freedom, which is going to be 12 minus 1, which is 11. So this means that on my table, I'm going to be looking in the row for 11. Then, because my confidence level is 90%, depending on whether you're at the top or the bottom of the table, you can use the percentages that are listed along the top or the percentages that are listed along the bottom. So I'm going to go along the top for 90%, and I'm going to go down to that row for 11. And it looks like we get 1.796. So my t-score is 1.796. All right, let's do a second example where we're going to find a t-score for a 98% confidence interval with a sample size of 76. So n is 76, and we've got 98% confidence. As before, we're going to find our degrees of freedom, which is 76 minus 1, or 75. Then I'm going to go to the bottom of the table this time, and 75 is not listed. So remember, I can't claim more freedom than I have, so I'm going to round 75 down to 60. I can't use 80 because that's too high. And we are looking at 98% confidence. So over here at 98, looks like, yep, 2.390. So our t-score is 2.390. There you go. That is how you find your critical values for t-scores. Okay. So this flow chart that I've got here recaps how we know whether we are using a z-score or a t-score. So the question that you ask at the beginning is, do you know sigma? In other words, do you know the population standard deviation? If you know sigma, then that means it's a z-score problem. So you just use the bottom row of that table, and here's your formula for margin of error. If you don't know sigma, that means you have a t-score problem. So then you have to determine your degrees of freedom, and then use those degrees of freedom to get the confidence, and the confidence level, to find your t-score, and then you use this formula for your margin of error. And then in the end, you're going to subtract your margin of error and add it to your point estimate. So let's focus on just that identification step, whether or not it's a z-score or a t-score problem. So the question we're going to seek to answer is, do we know sigma or not? In this first example, it says a simple random sample of size 18 has a mean of 71.32 and a standard deviation of 15.78. The population is approximately normally distributed. If I want to construct a 95% confidence interval for the population mean, will I use a z-score or a t-score? Okay, so first, I notice they're telling me that the population is approximately normally distributed, which I need to know because our sample size is smaller than 30. So we can still use our techniques. And they're telling me that S is 15.78. So they're telling me that my sample standard deviation, because that's what we use S for, is 15.78. In other words, we don't know sigma. So this is going to be a t-score problem. Now let's look at this next example. It says, Herbie finds the price for an SRS of 8 types of windshield wipers and records the prices below. Assume that the prices of all windshield wipers are approximately normally distributed. Okay, so this is again important because we only have 8 windshield wiper prices, so all of them are approximately normally distributed. So the population is normally distributed with a standard deviation of $4.18. If I were to construct a confidence interval, 99.5% confidence interval, for the mean cost of repair, would I use a Z or a T? So for this one, they're telling us our standard deviation of 4.18. So we have to determine whether or not this standard deviation is an S or a sigma. So as I reread through that sentence, it says, assume that the prices of all windshield wipers are normally distributed with this standard deviation. In other words, assume that the prices of all windshield wipers have this standard deviation. That means this is sigma. So since we know sigma, that means this is a z-score problem. So one of the things I want to caution you about is that when you make this identification, you really have to be looking for either the correct symbol or a full correct phrase. In this case, we want to look for either sample standard deviation or population standard deviation, or we want to be looking for the symbol of sigma or S. In some cases, that's easier to pick out than others. So here we use the letter S, easy peasy. Here we didn't, and so we had to identify using contextual clues what it was. We could have done that up here as well if I didn't write S equals here, because in this sentence it says, a simple random sample has a standard deviation of. So I would use a simple random sample has a standard deviation of 15.78. In this case, I'm ignoring the size and the mean because what I need to determine is the context of the standard deviation. You have to be careful because every problem you look at is going to have the word standard deviation. It's also going to talk about samples. It's also going to talk about a population mean or everything being approximately normally distributed. So in confidence interval questions, you will see the words population, sample, and standard deviation. You will see all 3 of them. What you need to figure out is which standard deviation is it? Is it a sample standard deviation or a population standard deviation? So the standard deviation is the clue, but just because you know a standard deviation doesn't mean it's z-score. Here we knew a standard deviation and it was t-score. Okay, what's important is which standard deviation it is. All right, so that's going to wrap it up for this video. In the next video, we'll go ahead and start finding some confidence intervals, and we'll begin by using z-scores. I hope you found this video helpful, and I'll see you in the next one. Bye for now, everyone.